2 weeks, 3 and 4 video for Calc 3. Didn't complete this problem, so let's go ahead and complete example 5. So we have to compute t prime of t, so we just do that over here component wise. Here's our t of t. So what do we get? 3 cos t, 3 sine t, comma 0. Then, got to compute the length of this vector right here. So 1 over root 13, square root, nine cos square t plus 9 sine square t plus 0. So we see that's 9 because sine squared plus cosine squared is 1, and square root of 9 is 3. So really we have 3 square root of 3 in the denominators. Square root of 3's will cancel. So I just get 1/3 there. So I get 1/3 times this vector, 3 cos t sine t, 3 sine t, comma 0, and we just multiply that through, get cos t sine t, comma 0, which is our n sub t. Okay, that's our unit normal vector. Next up, we'll be trying to find the unit binormal vector, and that's going to be found by finding b of t, and b of t is t of t cross n sub t. So we're going to need another slide here for sure. So I'm running out of space. So now we want to compute c, which is b of t, t of t cross n sub t. So b of t, of course, is going to be normal to both t sub t and n sub t, hence binormal vector, because you're taking cross product, right? So let's go back and see what we have for t sub t and n sub t. So t sub t is this vector right here. And I'm taking the cross product, right? So I'm just going to set up the cross product right away. It's row vector, so 3 root 13 sine t. Sorry if my writing's a little small. Negative 3 root 13 cos t, and 2 over rad 13 then I'm going to need n sub t, which is cos t sine t 0. Alright, now let's take the cross product. So we get 2 rad 13 sine t there's a minus there, I minus negative 2 over root 13 cos t plus 3 over root 13 sine square d minus a negative 3 over root 13 cos square d. Okay, we have to clean that up. So what do we get? Negative 2 root 13 sine t I plus 2 over root 13 cosine t j, and we need a k in here, cosine t j plus, looks like we have sine squared plus cosine squared, this is 1, so you get 3 over root 13, 3 over root 13, okay. And this is b of t, that's the binomial vector that we just found in standard basis form. You could factor out of 1 over 13 out of all this if you want to, that's fine. You could bring that out in the front, 1 over root 13 times these, that's fine. That's just by a constant. All right, and the last thing we need to find is d, curvature. You'll find that in your book there are a few different definitions for curvature, okay? We just have to use the appropriate definition to find it. And actually, shouldn't be too bad because we already found most of the components of what would make up the curvature. So let's go there and talk about curvature. So kappa k is equal to dt over ds, which is equal to t primes of t, the length of that, divided by the length of r prime of t. Now, nice thing is that we already computed t prime and r prime of t, so we can go back. We know the length of t prime of t is just 3 over root 13. And then the length of r prime of t is root 13 sine cosine. Okie dokie. So this is what we have. So this is like, you think of this as one big fraction if you want. You have a fraction here, you have a fraction there. You can flip and multiply it. So you're going to have 3 over 13 sine t cos t. That's kappa. That will give us the curvature for any t on this curve. So you can have t is pi over 4, for example, and compute the curvature. All right, let's look at velocity and acceleration, next topic. So we need to know limit definitions of velocity vector v, how to compute v, know a definition of speed and acceleration in terms of derivatives, compute speed and acceleration, be able to compute the tangential and normal components of acceleration, and understand Kepler's laws and application to the above. I'd just like to comment on the Kepler's law. Although we won't be tested on this concept, it is very useful to extend your knowledge in this area, especially if you're going into engineering or physics. Knowing how this applies to planetary motion is beneficial. Let's look at an example. So we have particle moves with position function given. Find the velocity, speed, acceleration of the particle. Sketch the path of the particle with the given position function and draw velocity and acceleration vectors for t is equal to 1. So we know right away that just to compute v sub t, which is a velocity vector, is just the derivative, just like normal single variable calculus, not much difference. So we just use the power rule here to compute that. And acceleration is just the second derivative of position vector. So we just take the second derivative there, which is not too bad. It's 12ti plus, it looks like just plus 0, so we could just write plus 0 here or just erase it. So it's just 12ti. By the way, if you don't have a j or k here, that means it's 0. So like here, r prime of t, this k component technically is 0k. This one would have 2 zeros and then 0j plus 0k. You usually don't write that, but it's implied whenever you have it not appearing over here. So that's velocity, acceleration. And then the speed. Speed is the length of r prime of t. We already computed r prime of t, so we just got to take the length of that. So it'd be 6t squared, quantity squared, plus 2 squared, plus 0 squared. But yeah, we don't need to write that if you don't want to. So what do you get? You get 36t to the 4th plus 4. Obviously, there's a GCF here over 4, so you get 2 root 9 t to the 4 plus 1. And that's our speed. I'll just call that, I don't know, S of t for speed. It says sketch a path of particle, given position function, draw velocity, acceleration vectors for when t is 1. So when t is 1, v of 1, what is that? V of 1 is 6i plus 2j. A of 1, what is that? A of 1 is just 12i. So these correspond to vectors 6, 2, 0. That's for v of 1. And for a of 1, it's just 12, 0, 0. Okay, so those are the vectors that we're looking at. So we just need to draw a little sketch. Now, one thing you'll notice here is the k component is 0. So technically, even though most of our work is in 3 dimensions, you could graph this on the xy plane because z is equal to 0, which is equivalent just to graphing on the regular xy plane. So we could let t be 0, 1, 2, 3. Typically t starts at 0, so that's why we're starting there. So let's just sketch this a little bit. So we get negative 3i plus 0j over here, so it would be just negative 3 on the x component. t is 1, you get negative 1, 2. T is 2, you get 8 times 2 is 16, so way over here. Minus 3, so 13. And it's going to be 4. Okay, etc., etc. I think we're kind of seeing the pattern. It's going to kind of look like a cubic. So something like this, just a sketch. And we're going in this direction as t increases, right? So, yeah, and you could go further and you can add more, like 1/2 in here if you want to be more precise. Going back, we see that we have 6, 2 when t is 1. So this, just remind yourselves that this is on the xy plane. So this is 6, 2 in the xy, so 6, 2 would be like something like so 6, 2, be like something like, it's not to scale. So this vector right here would be tangent vector. If I translate this vector up to this curve here, it should be tangential to it, although it looks a little askew because my this is not to scale. It should be a tangential if I bring this up here. And 12, so 12, 0, 0, when t is 1. So remember, when t is 1, that tells us we have negative 1 and 2. So we're looking at this point. When I translate this to here, it'll be the tangent. And here, this will be the acceleration vector. So really, this vector here is the acceleration vector. But if I translate that to here, I'm seeing we have a tangent vector that looks something like this. And then the acceleration vector looks something like this. That's 12. The magnitude of that vector is 12, right? And we can compute the magnitude of this vector as well. So this would be square root of 38, but again, this diagram is not to scale, so this is just to get a sketch of what we're looking at here. So these two are, this tangent vector here and this acceleration vector here is just to gain some perspective about what it looks like. Then we translate that to the point of interest, which is at x is negative 1, y is 2. All right, final example. We're going to be looking at finding the tangential and normal components of acceleration for the vector 1, 1 at 1, 1, 1 of the acceleration vector. So yeah, so we're going to need to compute r prime of t and also r double prime of t. So let's do that. Negative 1 over t squared I plus negative 2 1 over t cubed j plus negative 3 over t to the 4. Okay. Okie dokie, and we have to do it again. So we get 2 over t cubed I. That would be, c, we got plus 6 over t to the 4 j plus 12 over t to the 5 k. Now, the tangential component is given by this equation, r prime of t dot r double prime of t all over the length of r prime of t, and the normal, which is the second one, is r prime cross r double prime all over r prime, length of r prime. Fortunately, we're looking at 1, 1, 1, so all these t's are 1s, so it greatly simplifies our life. We get r prime at 1 is negative I minus 2j minus 3k, and r double prime at 1 is 2I plus 6j plus 12k. Alright, so now we just have to compute the dot product for the tangent and find the length of r prime at 1, and that would be at. So at is the dot product of these two. So I get let's write out the two vectors in component form. Negative 1, negative 2, negative 3. Dot 2, 6, 12. Over, and we're looking at the length of r prime of 1, and so just the length of this. So we get what, negative 2 minus 12 minus 36 divided by square root of 1 plus 4 plus 9. So we're just going to get negative 50 divided by square root of 14. So that's the tangential component of the vector at 1, 1, 1. And then we'll need to compute a ace of n, which is just the cross product of r prime at 1, r double prime at 1, divided by the length. So the length, that we could reuse that square root 14. We'll just reuse this. Here, and we'll change that to ace of n. And again, we're just computing the cross product. Now, a thing that's going to be different here, is this is still negative 50, wrong slide, is this cross product We just need to compute a determinant to figure that out. So we got I, j, k, -1, -2, -3, 2, 6, 12. So let's just minus -12 plus 6j plus -6 plus a -4, or minus -4, it's going to be just +4. Okay. So what do we got? We got -6i plus 6j minus 2k. So bringing that over here, we just have that this vector is like this. And we just need to compute the length of that. Hope I mentioned that earlier. Yeah, it's just the length. So it's length of that vector. It's just 36 plus 36 plus 4. So 72 plus 4, 76, root 76. This is from our old problem. So we have root 76 over 14. So that's the same thing as root 38 over root 7. You can rationalize that if you wish, or you can just leave it alone. Doesn't make any difference. So we'll just leave it be. So that's about it for this chapter review. I hope that you found it enlightening a little bit. You know, if there are other examples you want or other videos, please let me know. I'm all ears. So I'll see you next week. Take care.